Okay, if a force is any sort of push or pull on an object, what are some forces that could cause an object to speed up? Okay, having wind behind it, okay? Zeno? Okay, so what force is it that makes it speed up as it moves downward? Yeah, the force of gravity, right? So we're going to start looking at how that gravitational field applies. What are some other things that could cause an object to speed up? What if I push it? Yeah. Right, that would just be what we consider an applied force, right? It falls into this category of just applied forces. We're going to have to start labeling our forces with a lot of things, but the labeling lingo is a little bit, I don't want to say the word loose, but there's a lot of different ways you can label forces, right? But I like to give it a general category.
Can't you, like, for something to speed up or slow down, like, what would you call it if, like, is there like a whole different sort of field, I guess, for, I don't know, like a car or a bicycle or like something that you control the speed yourself?
Not necessarily. Nope. You would just have an accelerating force, like an applied force. We would call that applied force. Or if you apply the brake, we would just call that a braking force, right? There's just falls into a general category. So what are other ways that forces could cause me to slow down? Okay, wind in the other direction, what would we call that? Resistance, air resistance, right? Air resistance,
If you run into something.
Okay, good. If we run into some sort of object that stops us, right? Yeah, okay. What else? Friction, good. Okay, all of those things cause us to slow down. Okay, we've so far lived in this perfect physics world where air resistance and friction don't apply. And now we're going to start looking at scenarios in which they do apply, right? And how that causes our object to change its motion or its acceleration. Okay? All right, we've got to know a couple of different main vocabulary pieces here. The system is the object that's being manipulated, and the agent is the cause of the force. So if I push my calculator here, what's the system? The calculator, right? And what's the agent? Me, right? My hand. Okay, if I lift it or hold it, even me holding this object here, am I applying a force by holding it? Yeah, right? Because if I didn't apply a force to keep it upward, what would happen? It would fall, right? So I'm applying a force to counteract gravity, right? Or counteract the force of gravity there. So a lot of things that we might not think of as being forces really are, okay? So we're going to look at all that kind of stuff, right? Newton has three main laws that we study in the world of dynamics, okay? Dynamics is this major category of forces. And so Newton has three main laws. The first law we have a nickname for called the law of inertia. Have you heard that term before? Mm-hmm. Law of inertia. And it says a body at rest stays at rest and a body in motion tends to stay in motion. Does that sound familiar to you? Mm-hmm. Okay, that's Newton's first law. We see Newton's first law play out in our everyday world really often, right? Objects at rest stay at rest. Object in motion stay at motion. We often leave this part off of our kind of tagline for the law of inertia unless it's acted upon by an outside force. So those outside forces could be friction, they could be air resistance, they could be an applied force of some kind, but an object in motion will stay in motion or stay at rest. Do you know the definition of inertia? Okay, the definition of inertia is the tendency of an object to resist change. The tendency of an object to resist change. So can you think of another variable that probably lines up with inertia? Okay, let me ask that question in a different way. If I have a greater tendency to resist change, what does that mean I have more of?
Acceleration?
Kind of. Okay, we're almost in that realm. I want you to. I'm asking my question not in a very good way. Okay, let me think about this. Which tend to have more inertia, bigger objects or smaller objects? Bigger objects. That's what I'm trying to get to. The relationship between inertia and mass is really direct, right? Mass is essentially a measure of an object's inertia, right? Bigger objects are harder to start and harder to slow down once they're in motion than little objects, right? So an object with greater mass would have a greater tendency to resist change, right? Boulder rolling down the hill, much more difficult to stop than pebble. Agreed? Right? Or even a big heavy box. to get it started, it's much more difficult to start that box than a little tiny box, right? The greater the mass, it tends to be a greater amount of inertia as well. So mass is really considered the amount of inertia of an object, or vice versa, okay? But it's the tendency to resist change. So when we're at rest, we want to stay at rest, and when we're in motion, we want to stay in motion. Okay? All right, so as we start looking at drawing forces and representing forces, we need to understand that forces are a vector quantity. What are some other vector quantities that we've already studied? Yeah, go ahead, shout them out.
Velocity.
Velocity, what else? Two more. Acceleration, good. Displacement, good. Those are the three we've seen so far. Velocity, acceleration, and displacement. All vectors have to have both a magnitude and a direction. We draw them with an arrow, just like we've drawn them before. Okay? When we draw forces, their arrow is always in the direction of the motion. And we're going to do our best to draw them to scale. And remember, when we say scale, we're talking about a proportionate scale. So we want to make sure that if we have a force that's twice as large as another, we draw it twice as large as the other. We have a unit for force of newtons, and newtons is a derived unit. So it's like a nickname for the unit kilograms times meters per second squared. Bless you. That's the real unit for force, but we condense that unit down to a unit called a newton. Okay? Can you tell me what are those two units used to measure? Kilogram times meters per second squared. What do those represent? Mass times acceleration is going to be the way we solve for force. So we're going to see that equation actually here in just a minute, okay? And so the unit for the unit for force is kilogram times meters per second squared, but we abbreviate that down to call it a newton. Okay? When we start drawing forces, we're going to use what we call free body diagrams. And we're going to look at those here in a second. But they're really simplistic diagrams that just have to include all of our forces as vector quantities. So we'll represent our forces with arrows and things like that. Okay? Okay. Two main categories of forces. They fall into two major categories, and then there's a lot of different separations from there. But there are contact forces and field forces. They are opposites of one another, right? What do you think a contact force has to have? We have to make contact with our system and our agent, right? Our system and our agent make contact between one another. So this is any sort of applied force. Okay, any sort of applied force here. Let's list some other things. So applied forces would be any of these examples of pushes or pulls. Is friction an applied force, a contact force? Yeah. I think so, right? We can't have friction if we're not, actually coming in contact with our object. That's what friction is. Okay, any other applied forces that you can think of, right? I'm sorry, I said applied, but I mean contact. Applied is a giant category. So there's a lot of things that fall into the category of applied forces. Push, pull, braking, accelerating, all that kind of stuff. Then field forces are the opposite of that. So field forces are forces that can be exerted without contact. So the main one here is a gravitational force. Okay, any other things that you can think of that would fall within that category? Magnetic, yep. The magnetic field would fall within that category. We don't study magnets a whole lot, but that magnetic field does fall in with that category, right? Non-contact types of forces. Okay. Any questions with that? Okay. Okay. We're going to start looking at when we put all of our forces together, we have what's called the net force. Do you know what net means? Net profits, net income, what does that mean? Yeah, the sum of or overall. So we're taking positives minus negatives, right? Anything that's coming in minus outgo would be that's the net of something. And so when we have a net force, we're going to take the sum of all the forces acting on our object, and it will give us the result of a net force. We have net forces in both the X and the Y direction. We need to understand that even in this chapter of forces, we analyze our horizontal and our vertical motion separately just like we did with projectiles, we have to keep horizontal and vertical motion completely separate, because we can accelerate in the vertical direction or the horizontal direction here, but not in the same way, right? We have different objects accelerating horizontally and vertically. So we have to make sure that we keep our X and our Y separate. So you might have net force, F net, in the X direction, or F net in the Y direction, okay? All forces will be labeled with a capital F, and then a subscript describing what type of force that might be. Okay, so F net will just be net force. Then you can even tag an extra little subscript on there. So you can kind of label them as detailed as you want. Some books and some programs go into crazy labels for their forces. I try to keep them pretty simple as to what they should be. Say it again.
What would like the more complex ones look like?
When they're labeling the force, it just depends on how the books label it. But some say, okay, so if I'm talking about gravity, I label it FG with a little gravity, just like that, little g. Okay, some would say this is the force of the earth on the object, right? And they label it like that. That's too much for me, right? I don't need that much happening in all my problems, right? So yes, gravity is the force of the earth on our object, right? We agree with that. That's what gravity is the gravitational force between the earth and the object. But I don't need to write that out, right? I know what gravity is. And so that's what I'm talking about. Some of them go way too detailed into their labeling, but we're going to try to keep things simple. Okay, and we'll still understand what that means. Okay. Do you have any idea or thoughts about what this word means? An object is at equilibrium when it's at rest or when it's moving at a constant velocity. What do you think that equilibrium means? Yeah, Isaac.
Like balance.
Okay, good. Yep, that's what we mean. If we're at equilibrium, the net force in that direction, that doesn't really look like a net, the net force in that direction equals 0. Okay, and so that means that our positive forces and our negative forces must cancel each other out. They equal each other. Okay, that would mean that I have an acceleration of 0. Okay, if my object is at rest or if my object is at a constant velocity, I have a net force equal to 0. Okay? If it's at rest or if it's at constant velocity, because we're going to show you an equation for net force here in just a second. But essentially, net force on any system is the object's mass times its acceleration. Okay, you can go ahead and write that down. I'm going to have it again on a couple slides, but the net force of any object is calculated by taking its mass times the overall acceleration in the horizontal direction or the vertical direction. And so if I'm at rest, my acceleration would equal 0. Or if I'm at constant velocity, my acceleration would equal 0, right? Which would then lead me to that. Yeah.
Is there ever something at constant velocity in the not perfect physics world?
Yeah. Mm-hmm. Yeah. We're going to talk about today something called terminal velocity, which is when you fall for long enough that your air resistance force and your gravitational force equal. So you stop speeding up as you fall. You just fall. Right? But there's lots of things that move at constant velocity in the real world. Yeah.
Is that why, like, you can't, a penny drop from, like, the Eiffel Tower or the Empire State Building, the terminal velocity?
Mm-hmm. Okay, that's all. So if I have an object, I'm going to show you a little diagram here. If I have an object that's sitting on a table, and when we draw force diagrams or free body diagrams, we represent our objects with a dot, thank goodness. Okay, they don't have to be more artistic than that, okay? Because I don't have it in me. Okay, I've got gravity pulling me downward. Actually, I'm going to introduce a couple more things before I draw that out, because there's a couple things I need to draw that we haven't seen yet. Let's go ahead and look at our free body diagram here, okay? When we draw diagrams, we need to, when we have force problems, we need to draw the diagram called free body diagrams. We have to identify every place the system has a force acting on it, so every place it does, and then we need to draw forces as vectors in the direction of the force stemming from the object. Okay, so let me make this clear. In this system, the hand is pushing the book to the right. Are we understanding that? Our force is drawn like this and not like this. Okay, we're not drawing our force into the system, right? We're representing our system with a dot, but we're drawing our forces stemming from that system, not into our system, okay? There are two other forces drawn on this book that we've only introduced maybe one of them, okay? Force of the Earth's mass on the book, okay? I don't need to write all that out because what is it that's pulling the book down? Gravity. This would be, I would call this the force of gravity, right? Which that's what the gravitational force is the mass of the Earth and its relationship to this book, right? It's going to have enough gravity to pull it downward. This force is something that we haven't talked about yet, but it's the force that is the table pushing back up on the book, right? The book is being pulled down by gravity, but the table is exerting a force upward on it to keep it upward in its upright position. Right? This I call, and not just me, I didn't make it up, right? This is what it's called, is the normal force. Okay? So we label it F capital N is called the normal force. And the normal force is exerted by any surface, floor, ground, table, whatever it is, to counteract gravity, essentially, right? If the book is pulling down on the table is then exerting an opposite and equal force up on it. Have you heard that? For every reaction, there's an equal and opposite reaction. Have you heard that term? For every force, there's an equal and opposite force. That's Newton's third law. We're going to talk about that here in just a second, okay? But that's called the normal force. So tell me, in this system, do I have an axis that is at equilibrium? Is vertical forces at equilibrium or horizontal forces at equilibrium or both? Just vertical, right? My vertical forces are at equilibrium because my object right here, is it accelerating vertically? No, that's the only question I have to answer. Is my object accelerating vertically? And if it's not, then I know that these two forces are congruent to one another. Do you know what those lines are when I draw those? You know what those mean? Congruency lines, have you seen those before? Okay. These are congruent to one another as long as my object is not accelerating in the vertical direction. And we would agree here in this case that it is not. Is it accelerating in the horizontal direction? I would think so, right? As I push the book, we don't know what the force is pulling it, but if there's nothing opposing that motion, which in this there's not, right? We don't see friction in this diagram. If there was, our friction would oppose the motion in that direction. But it's not drawn there, so we're assuming we can ignore it, which means my book would be accelerating to the right. Do we see what's happening in that image? Okay. All right. I would never call that either. I would just call it force APP for applied. Right? There's no use in me writing out 4 extra words. No, thank you. Okay. I would call that applied force. You can name it FP for push. I don't care. Right? But that's just what I would call it. Okay. Remember, we want to draw each and every force that we see. We're going to try to draw them to scale, and they should always be pointing away from our object. Okay? Always stemming from the object and pointing in the outward direction. All right, so let's try one here. Draw the free body diagram of a box accelerating in the rightward direction and include frictional forces. Okay, I assume here that the box is not floating in midair, right? That it's setting on a surface of some kind, okay? So let's see what that would look like. Luckily, we don't have to draw a box. The dot is plenty sufficient. I always know I've got a force of gravity. And if I'm on a surface, that means I must also have what? The normal force, Okay, it's accelerating to the right. Do we really know what's making it move to the right? Nope. No, but I'm going to put it into some sort of applied force category. So I'm just going to write F applied. And then I have to include frictional forces. Which way will friction be going?
The opposite.
It will oppose my motions. Will my frictional force be greater than, less than, or equal to my applied force?
Less than.
Less than. How do I know that? It's accelerating in the rightward direction, which means this force must be greater than my frictional force. So those two are not equal. What if it had said it's being pushed to the right, but moving at a constant velocity? What would have to be true about my frictional and my applied force there? They would be equal, right? If it was at constant velocity, that would tell me that those forces would need to be equal to one another, but it's not at constant velocity. So we want to make sure that our frictional force is shown to be less. Friction is just given with a lowercase f, right? Force of friction. If I want to be really clear about my diagram, I'm going to go ahead and mark those congruency lines. You don't have to. That's not an absolute necessity, but it gives me a clear indicator of that I know it's not accelerating in the vertical direction and that I know it is accelerating in the horizontal direction. Okay, again, not something that is an absolute must, but I think it's good for you to understand when those are equal to one another. Okay, what about this? A car is coasting in the leftward direction and slowing down. Okay, I've always got gravity, and we are assuming here our car is not floating in midair, which means it's on a road. Okay, so I've got, oops, not friction there, the normal force, right? Because the road is applying a force equal to gravity in the upward direction. What happens when you coast? Are you applying a force to move yourself forward? No. So what's the only thing causing me to slow down? Friction. Okay, and so I'm coasting to the left. So what way must friction be going?
Right.
To the right. Okay, so force of friction here. Okay, I know my car is not accelerating vertically, which would mean those two are equal to one another. Is my frictional force necessarily equal to the other two? No, because we analyze vertical and horizontal motion completely separately. So there's no need. I wouldn't mark that as congruent because I just don't know. Right, I wasn't given any numbers. Okay, we feel comfortable with drawing basic diagrams like that? Always gravity. If we're on a surface, we've always got normal force. We said that, okay? Let's look at how can we calculate simple net force. Net force is the sum of the forces of our system. We take positive force minus negative force. Okay, that's how we calculate net force. Positives minus negative forces. And which direction do we consider the positive direction? Right or left? Right. Okay, so this would be the positive forces and this would be the negative forces. So if we have a free body diagram that shows us a rightward and a leftward force, each of 100 newtons, our net force comes out to be 0. Do we agree with that? Right? It's like a tug of war situation, right? If we're both pulling with equal strength, it's not going anywhere. Yeah, go ahead, Isaac.
So are we subtracting a negative?
Yeah, so I would, this is what my net force equation would look like. And we're going to set this net force equation up really often. I would say this, F net is equal to F1 minus F2.
So I don't put,
So I would just go 100 minus 100.
okay, so I don't,
Yeah, I'm not going to put in
F2 is
minus
not-
negative 100.
Okay.
Yeah, good question. Okay, so I just take all my positive forces, subtract all my negative forces. Okay, we're going to set up this equation a lot. Positive forces minus negative forces. So we're going to get really good at being able to identify which ones are moving in the positive direction, which ones are moving in the negative. So when I say your net force equation, it looks something, looks something just like that, right? Positive minus negative.
can a force have negative values?
Yes, that would mean it's moving to the left or south, depending on which ones you're looking at. Yep.
So for F2 there,
Mm-hmm.
it says 100 and,
If it was 200, I would take 100 minus 200, and my net force would be negative 100 newtons.
okay, I see what you mean. But we shouldn't mark F2 as negative 200.
No, you can think about it either as negative 200, or you can just think about as this is the negative direction, and then here's all of our forces that are moving in the negative direction.
Right, but what about like answering the problem when they ask us what F2 is?
Yeah, you could say 200 newtons west, or you could say negative 200. Either is fine. Yep. Because the negative, remember, it's not a numerical value. It's a
Right,
directional.
it's
Yeah. Okay, let me show you on the second one. If this was me, if this was my free body diagram, I would say you have a F1 and then you have F2. We can draw them stacked, right? One on top of the other. So when we draw our free body diagram, we would put them one right next to the other. So if multiple forces going in the same direction, we would draw them tail to tip, just like we've practiced before. Okay, so in this case, my net force equation would just say my positive forces added together Do I have any forces in the negative direction? I don't. So you can put a minus 0 on there to make you know you thought about it, but you don't have to. So my net force would be 200. Okay, do we feel comfortable there? Okay. And then in my last one here, my net force equation would be F1 minus F2. And so here's that situation we kind of drew up. 100 minus 200, which means our net force, 100 newtons, and they went ahead and drew the arrow. I would accept negative 100 newtons or 100 newtons west, right? Either way would be an acceptable answer for that final net force. Okay, but this part right here, drawing that net force equation and writing that up, is always going to be positive forces minus negative forces. Okay, so if we were talking vertically, we would go upward forces minus downward. Okay, so that's why the diagram is so important, because you have to, once you have the diagram there, it's really easy to see what are your upward or what are your positives, etc. Okay? Are we hanging in there? Doing okay?
Yeah.
All right. I have to, here's what I want, says a lot of words to essentially get to this equation. All right? It says the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. The direction of the acceleration is in the direction of the net force acting on our object. So essentially, our equation boils down to this. Newton's second law is F net equals ma. That's the one I drew up for you earlier as well. So now we have two different ways to be able to calculate the net force. We've drawn up two ways to calculate net force, haven't we? Mm-hmm. So we said that net force can be calculated by taking positives minus negative forces, and we know that F net can be calculated by taking mass times acceleration. So can you guess what we're going to do here a lot of times?
Yeah, fine.
We're going to set them equal. We're going to substitute a lot of times, and we're going to be able to say the mass times acceleration of a system is equal to the positive forces minus the negative forces. Okay, so it looks funny with this, but when we start putting numbers in, it's going to make sense, right? We're going to be able to transfer that in. But this gets substituted up here in our net force equation super often, right? Because it tells us the acceleration of our system that is a result of those net forces. Okay? So we're going to see this F net a lot. And we already talked about its units, so we're good to go. Okay. Find the net force needed to accelerate a 1,000 kilogram car at 4.9 meters per second squared. Find the net force needed. So that means it's going to encompass whatever forces are actually acting on the car. We don't even care. We just want the net force. And so it's really as easy as it seems. F net equals mass times acceleration. Right? It's actually just that easy. 4,900 what? What would I label my units? Newtons. Good. Okay, good. Go ahead and grab your calculator out if you don't have that yet. We're going to do a few more calculations here as we get going. 4,900 newtons. And my acceleration was positive, so I assume my net force is positive. I don't know. I assume it's east, right? Because it's talking about a vehicle, so it's horizontal. But I can't put in any more information than that, right? I just can leave it as a positive. Okay. So simple. There could be a lot of forces that are acting to equal that net force, but we're not concerning ourselves with that because it just wants the net. So that could include applied and brake and friction and whatever. We don't know that. Okay. What net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? Okay, so we ramped it up a little bit here from question 1 to question 2. You might even need your kinematics equation to help you solve. Ding, ding, ding. Okay, right? Kinematics, fortunately or unfortunately, maybe you love them, they're not going away. Okay, so we got to make sure that we are still able to use those kinematics equations. Okay, what net force is required to bring a 1,500 kilograms, so that's my mass, car to rest from a speed of 100 kilometers per hour with a distance of 55 meters. So if this is my equation, F net equals mass times acceleration, I need to find what for this vehicle? I got to find the acceleration. What's the acceleration on the car to be able to find out what the net force is to bring it to a stop? Okay, so I'm going to convert my kilometers per hour to meters per second. Do you remember our shortcut there? Divide by 3.6, good. And so that gives me 27.78 meters per second. That would be my initial velocity. And my final velocity would be equal to 0, right? Because I want to bring it to rest. Okay, I was given a distance of 55 meters, which would have to be my x final. All right, so if I'm looking for a kinematics equation, I would probably choose which one? The third. Good, I would agree. So 0 squared equals 55 squared. No, not 55. What am I doing? 27.78 squared plus 2. Can I use negative 9.8 for A?
No.
No. Number 1, it's horizontal, so no. And number 2, that's what we're solving for. Oh, at least 55 is in the problem. I thought I was making up that number out of nothing. Okay. Squared. Okay. What did we get for our acceleration? Good, negative 7.01. So we can just take that to negative 7 meters per second squared. Okay, does it make sense to us that our acceleration is negative? Does that track?
Mm-hmm.
Okay, and then so if I want my net force, I would take mass times acceleration. Oh my. And I get a value of 10,500 newtons. And my force here will be negative. All right, so let's talk through why is my force negative here? Or does that make sense? It's bringing it to a stop, right? It's opposing my motion. Right? So if I'm moving in the positive direction and I'm slowing down, my net force has to be slowing down. So it could be a combination of a braking force and a frictional force that's slowing me down. But that net is in the negative direction because it's opposing my motion. Okay, so we feel comfortable with that? So negative 10,500 newtons. I wish I had a threshold or expectation for forces, like they can only be within this range. No, forces can be really tiny or really big. So I can't give you like a threshold as to like we're going to get really small numbers when we do these problems or really big numbers. It's just not something that we'll see a pattern with. So you can expect, right? You're going to see, you'll be able to kind of figure out what we should be expecting, but yeah.
So like what's a relative for, like if I were to
Vertical systems now. So we've looked a lot at horizontal. Now we're going to look at vertical systems and how gravity might affect what's happening here, okay? We talked about mass being a measure of inertia a little bit earlier. And that does kind of fall into its definition here, okay? Mass is a quantity of matter or a measure of inertia. Kilograms is our unit for mass, always. Okay, always kilograms. We oftentimes use the terms mass and weight interchangeably. Would we agree with that? Which term do we use more often just in our everyday language? Weight. Okay, however, it's incorrect. Us using the word weight is incorrect because weight is a measure of how much gravity is acting on our system. But mass is how much atoms you have there, right? The actual mass of your atoms. And so weight is actually a force. It's not just a measured quantity. Weight is a force, and it's how gravity affects our mass. So when we go to the moon, we weigh less on the moon. I would agree with that. I don't even need to put it in quotes. We actually do weigh less on the moon. But do we lose actual kilograms when we go to the moon? No. What's happening when we go to the moon? Right, gravity is different. The Earth's mass, we're farther away from the Earth, significantly farther away from the Earth. So the mass of the Earth affects us significantly less when we go to the moon. And so we weigh less. We don't actually lose kilograms, right? We might because of the diet we have to use when we're there, but we're not losing kilograms the second we go to the moon, right? We're actually just weighing less. So we need to understand the difference between them. Weight is always going to be a force, and it will be measured in newtons, and mass will be in kilograms. So we need to understand if it says an object has a weight of 400 newtons, that means it already did some of the math for you. And so we're going to look at that here in just a second. Weight is another way to represent the force of gravity. Okay, the force of gravity. Okay, so weight would be equal to Fg. Luckily, it's super easy for us to calculate. Okay. Okay, so weight is essentially using Newton's second law, but instead of acceleration, we're just going to plug in little g, which is the acceleration due to gravity. Do you remember what the value is for the acceleration due to gravity? 9.8, right? And it's 9.8 meters per second squared. But what's the caveat there? It's 9.8 when we are where? On Earth, right? On the surface of the Earth. So if I go somewhere else, to the moon, my g value would not be 9.8 anymore. It would be 1.7, roughly. 1.6 something, okay? 1.67, yes. Yeah, roughly. Okay, but that value would change. So Fg is weight, or we can call it the gravitational force, but we're going to take mass times 9.8 as long as we're on the Earth surface. Okay? Once we do this math, we would be measuring that value in newtons, right? Because this is kilograms and this is meters per second squared, which we said gets us to our unit to be in newtons. Okay, so tell me, let's do this one. What is the weight of a 60 kilogram crate? Right, when I'm solving for weight, that means I'm solving for Fg. So I take mass times gravity, which means I'm taking 60 times 9.8. Okay, so 60 times 9.8 gives me 588 newtons.
Is gravity not negative because you can't have weights?
So that's a great question. Weight is going to be pulling us in the downward direction always. And so we'll take care of that negative when we set up our net force equation. F net equals positives minus negative forces. Well, the negative will be taken care of right there. Yeah, that's a good question. So we're not going to plug in negative 9.8 when we do our value. We'll just plug in 9.8. And I will tell you that AP uses 10 as the acceleration due to gravity. And so that makes our math a lot easier, right? We would just call that 600 Newton weight. Okay, so you'll be able to make that calculation a little bit quicker on the AP test, is that they use 10 instead of 9.8. Uh-huh.
How are newtons in like pounds?
Yeah, okay, I actually don't know the exact conversion of that. You have a conversion between pounds and kilograms, right? And so you would have to do a conversion and then put acceleration on it. Okay, but like what our scale actually reads for us, that's a little bit trickier, but I'll have to look up. I don't know what the exact conversion is between newtons and pounds.
Wait, why wouldn't...
So we said normal force applies from any surface. So the ground, the table, the road, the whatever. Normal force will go always perpendicular to the surface. So let me say that again. The normal force always is perpendicular to the surface. So even if I have an object that's sitting on an incline, here's my object. My normal force looks like that. But what's my gravitational force always pulling? Always straight down. So in this case, are they exactly opposite of one another? No. And so we're going to look at how we deal with that situation a little bit later in our chapter. But normal force always is perpendicular to the surface. Okay. And then gravity is always pointing straight down. So for objects that are on a horizontal surface, it makes it nice and easy, right? Gravitational force is here. Normal force is here, right? No problem. But when they get on an incline, then some different things happen.
Is that why stuff falls down on an incline?
Yes, sometimes does and sometimes doesn't,
What?
right? On an incline, do things always slide? Or sometimes do they sit? Sometimes they sit. It depends on how steep your incline is, depends on how big your object is, depends on your friction on the incline. There's a lot of things that can depend on whether or not an object will slide down the incline. Okay, will friction ever cause something to move up the incline? No, right? So we'll have situations in which our frictional force is greater than our gravitational force, which means it's not going to move up the incline. It's just going to stay put, right? Our applied or our gravitational force is not enough to get it into motion. So we'll look at that. Inclines are really interesting, but we're not there yet. Okay, here's where we get into some actual calculations here with normal force. So let's go ahead and look at this diagram. There are 3 situations here that's happening in the diagram. And I don't love the way the book drew this diagram, so I'm going to kind of draw over it, okay? Here is my object. I'm just going to draw it here in the center. You can draw your free body diagram from the table. It makes no difference, okay? But in my object here, I've got gravity. Why do you think they labeled it mg?
Mass times gravity.
It's the same, right? That's the same as labeling it FG, but I won't ever do that. I don't know. This book, I don't like the diagram, but I like the problem. Okay? And then I've got a normal force here. Okay? In this situation, let's say that our box, I want to say that our box has a mass of 10 kilograms. Okay? And in each situation, our goal is to calculate the normal force. Okay, so for every scenario here, our goal is going to be to calculate the normal force. Oh, you can't see that very well, sorry. The box has a mass of 10 kilograms, and our goal is going to be to calculate the normal force in every scenario. Okay, so we're going to have 3 different situations here. In my first option, if I set up my net force equation, what is my upward force here? Right, the only positive force I have is the normal force. And what's my downward force? Fg, right? Do you see how I'm setting up my net force equation? Positive forces minus negative forces. We agree? Okay, so my goal is to find what is the normal force, right? This is my goal. I'm calculating this value. Can I calculate Fg? Yes, I can take mass times 9.8. I don't know what normal force is, so I'm going to leave it there. Is my box accelerating in the vertical direction here? No, which means my net force would be equal to 0. Okay, and so now I've just got a situation that says 0 equals normal force minus 98. And so that means my normal force is equal to how many newtons? 98 newtons. We agree? Okay, we see how that math works out. We could have calculated that probably a little simpler if we had just done, our congruency lines and figured out our force of gravity was 98. So normal force has to be 98, right? But I want us to get into the process of getting this equation because we're going to use it really often. Okay, so that will work in all situations. All right, let's look at our second one here. We've got 3 different forces happening. We are lifting the box or attempting to lift the box off the table here. But do we agree that it's still resting on the table? Right, we're pulling upward, but we're not doing enough to get it off the table. So here, this is the same scenario. I'm pulling upward on my cup, but I haven't done enough to get it off the table yet, which means there is still a normal force present. So my diagram, again, I'm going to draw it differently than them. Fg, we've got a normal force. Can you see that red pin okay? And you've got an applied force, a lifting force. Can you see me drawing over that diagram? Is that okay? Okay. So I've got 2 upward forces here, my applied force and my normal force. So in my equation down here, I would say F net is equal to applied plus normal minus gravity, right? I'm taking both of my upward forces, they're added, and my negative force is going downward. Can we set up that equation on our own, you think, based on the diagram? Okay, so let's keep going here. Is my object accelerating vertically? No. So net force is 0. Applied force is 40. I'm solving for the normal. My FG didn't change, did it? Because my box still weighs 10 kilograms. So in this case, I would say 0 equals Fn minus 58. So my normal force is equal to 58 newtons. So tell me, does that make sense? As I'm lifting up on that object, is my normal force having to work the same, less, or more than the first situation? It's having to work less, right? Think about that. As I'm lifting up, I'm like taking some pressure off the normal force, right? So that's what we need to be thinking about that. So it makes sense to me that our normal force is less than our original situation. Okay, in the last one, what are we doing to the object? Pushing down on it. So what can we expect for our normal force to do? It's going to get bigger. It's going to have to work harder, right? I'm applying more force to it, so it will have to work harder. So my equation looks something like, or my diagram looks like this. Fg applied because it's being pushed downward and normal force here. So can I draw any congruency lines? Is my normal force and my gravitational force equal anymore? No, because I've got more things happening. Okay, so net force is equal to normal minus Fg minus force applied. Right, do we see? Because both of those are going downward. It's not accelerating. Normal minus 98 minus 40, which means my normal force is equal to what? 138 newtons. Should my normal force ever come out negative? It should not, because it's pointing upward, right? And so I sped up the math a little bit there, right? On the algebra, we're going to have to move it to the other side, blah, blah, blah. But our normal force should always come out positive. If your normal force came out negative, what would that tell you? Okay, almost. No, it means that I've applied enough force to lift it off the table, so I don't have a normal force anymore, right? So if my normal force came out negative, that would be a red flag to like that fact that it's not even on the surface anymore, so my normal force would be negligible, right? I wouldn't have one. Okay. Through this scenario here, how many of you go fishing? Right? Big fish on the line. What happens if I pull too fast? It could snap the line, right? But if I reel it in slowly, is it going to snap the line most likely? No, it has to do with the acceleration on the line. So if I pull it slowly, right, it can make it. It can withstand that tension. But if I try to max out the tension by a big acceleration, it's too much, right? So it has to do with not just the mass of the object, but how much tension that rope or cable or string or whatever can withstand, right? Okay, so let's draw our diagram here. I'm raising my bucket. So here's my bucket. I've got a force of tension, and I've always got gravity. Do I have a normal force in this scenario? Nope, because I'm not on a surface. I'm suspended. Okay? My net force equation, F net, would be equal to the force of tension minus the force of gravity. All right, my goal is to find the acceleration. So what can I substitute right here for F net? Mass times acceleration. So MA equals force of tension. It says it can withstand 50 newtons. Minus mass times 9.8. I forgot to go ahead and plug in my mass over here on this side. So this is also 5 kilograms. Do we see where those numbers are coming from? Right? The tension I can withstand is 50 newtons. So I'm going to go ahead and plug that in to tell me that in order to get 50 newtons worth of tension, what can my acceleration be? Okay, so 9.8 times 5 is 49. 50 minus that divided by 5. So my maximum acceleration comes out to be 0.2 meters per second squared.